Thank you, everyone. Welcome to today's session on understanding large language models. Um, I'm Abhishek. I'm a research engineer with DeepMind, where I've been working on large language models and also vision language models. For this session, we'll try to go over the basics mechanics that are used for running large language models. We'll start with a quick intro and go over some of the applications that large language models have been used for and their impact. And we'll do a quick case study of one of the large language model, followed by understanding or a very high level overview of the transformers, which are the basic building blocks of the large language models. And then we'll look at how we can train a large language model from ground up, and then sort of followed by the challenges and some of the limitations that large language models can have. So let's try to understand what are large language models. Let's bisect this problem into language models and the large. So language models are the machine learning models that have the capability to predict the most likely occurrence of the next word given a set of words. So basically it does that by determining the probability of a given sequence of words occurring in a sentence based on the previous set of words that have been given to it. So in short, it has the ability to complete a sentence. Now that's a very basic definition of the language model. And the large part in the large language model refers to the data set and the parameters they have been trained on. So large language models are generally trained with very huge set of data sets, terabytes or petabytes of data, and the large parameters refers to the trainable parameters that a model has that are trained while training the model, and the number of parameters determine the size. So for example, PaLM is one of the large language model which we will take a look at in the following slides. It has about 540 billion parameters. The models that were being used before these were less than 1 billion parameters. So we were dealing with models which had around millions of parameters, but large language models tends to have parameters in terms of billions. And here are some of the applications. This is not an exhaustive list, but recently LLMs have revolutionized the conversational AI space, where we are using them for the chatbots, for building various types of chatbots. They can also be used for question answering, where given a context or a text which serves as a context and a question about the text, then language model have the ability to answer those questions. They can also be used for summarizing a chunk of text or long paragraphs or documents, and they have the ability to generate a short summary or a longer summary, depending on how you train them. And they can also be used for machine translation task, where you give the input in a particular language and ask the model to generate the translation of the text in a target language. Similarly, very similar to machine translation, they can also be used for code generation, where you prompt the model to either with a problem to generate the code, or you can also ask the model to translate the code into a different programming languages. So one pattern we can notice is large language models are really good at generative AI kind of generative text problems, and these are not the exhaustive applications. Like you can also ask the language model to write poetry or stories or come up with other text given a context. So that was a very quick overview of the applications. Now let's jump into one of the large language model called Pathways. It has been released by Google Research, and it's a Pathways language model. The dataset that they used for this model consisted of English and multilingual web documents. They also used the Wikipedia articles to train the model, and also consisted of some conversational data, and also the code from the GitHub website, which is generally has open source projects, and also the code from other companies on GitHub. The architecture that they used was a dense decoder only transformer model. We will, in the following slides, we'll try to understand what are the different types of transformer models, so please bear with me until then. But For now, we can go with this. And the number of parameters that this model had was 540B, as we mentioned. And this was trained with the pathway system. So pathway system is a sort of the infrastructure that Google used to train this model. It was optimized specifically to be able to train a very large language model. In simpler cases, we are not training a large language model, just a simple transformer with only few millions of params. You would be able to train them on just GPUs or TPUs, but training such a large language model at such a huge scale with 540 billion parameters, there were certain techniques required to be able to update the model, collect the information that every part of the model was learning, and then aggregate that and update all the parameters accordingly. So they developed the pathway system for that. And some of the tasks that it was trained on were language understanding and generation. This includes question answering, summarization, machine translation, etc. And it was, since they also trained it on the code data, it also had the code generation capability and common sense reasoning. So here is a quick snapshot of some of the responses from the models for different tasks. For example, on the left we have the prompt where we are asking the model to generate the code. So it was able to do that without any issues. And on the right top, we have a prompt where we ask the language model to identify the name of the movie given the emojis. So it was able to correctly identify that. And at the bottom left, there is the question that involves some kind of common sense reasoning. So we asked the model which of the following sentences makes more sense between I studied hard because I got an A on the test versus I got an A on the test because I studied hard. So model was able to understand the nitty-gritty between of the language semantics and was able to respond with the correct answer, which is I got an A on the test because I studied hard. So that's just an example of the pathways. Now let's take a look at the transformers, which are the basic building blocks of the large language models. So transformers are machine learning models that were trained to solve sequence-to-sequence tasks while handling long-range dependencies. Let's dissect this. So sequence-to-sequence task refers to your input is a sequence of words, and then your output can also be a sequence of words. So for example, if you take summarization as the task, then your initial text document that you're giving to the model is a sequence of words. And then the response that you get from the model is a summary, is also a sequence of words. And the long-range dependencies refer to the length of the text it can handle. The previous model, previously we used to rely on recurrent neural networks, but they suffered from long-range dependencies, as in they were not able to retain the context as the length of these sentences grew. So for example, they did not work well for long documents or long sentences, and they had the tendency to forget things that were being, forget the information that was present in the beginning of the sentences towards the end. So that is where transformers came in and sort of tackled the problem of dealing with long-range dependencies. Transformers are much better at retaining information, long-range information present in the text. And as we sort of increase the size of the transformers, by increasing size, I mean increasing the number of params, and they're built on like the layers that they use can be treated as Lego blocks. So you can stack multiple layers on top of each other and get a bigger model. So here is a bird's eye view of the transformer model architecture. We'll try to first look at the encoder side, which basically, in the interest of time, I will not be going into the detailed mathematics, but just kind of give an intuition behind the encoder architecture. So the idea is, here you present the encoder with an input. It can be the text, long document, or anything, and then it would give you an embedding or a representation of the text that the model can understand. Now that representation that comes from the encoder is used by the decoder, and that generates the output words or the tokens by reading the embedding that came from the encoder. So the mechanism that encoder and the decoder they both have in common is called the attention mechanism. Very high level definition of the attention is basically through self attention or attention, the model tries to learn the important words that are associated with certain words in all the words in the given text. So for example here, the important words for the word making are making more difficult, and then and 2009. So through attention, the model is able to learn the importance of other tokens with respect to a particular word. And this is done for all the tokens, and then this is done multiple times. So every layer is doing this process, but doing it repetitively, and every layer will come up with a different kind of representation of the text, because the previous layer had given certain different type of representation. So every layer will try to focus on different aspects of the text, and that's how a model sort of learns to understand the semantics of the language by doing this multiple times. And on the decoder side, the representation that comes in, it has one additional attention layer, which basically, so decoder has its own attention, and then the attention between the encoder and decoder is also part of the decoder, where decoder tries to understand the important parts of the embeddings that are coming from the encoder. So let's take a look at different types of transform models we have. So the original transformer has encoder and a decoder, but we have also trained encoder only architectures where there's just encoder. So BERT was very popular, which is encoder only architecture. And then we have decoder only architectures such as Lambda. We'll take a look at Lambda later, but let's try to understand how we can actually train a large language model from ground up. So it involves two steps. First step is the pre-training the large language model from ground up, where you try to train it for a particular task, and then train it on a huge data set after the pre-processing has been done. So pre-processing, you basically tokenize the inputs to the model into smaller chunks, and the training objective could be either predicting the next word given a set of words, or you can hide some of the words and then ask the model to come up with those words. So these two, and then once you have pre-trained the model, you can further refine it towards a specific task by fine-tuning it. So fine-tuning, you can think of it as a person who's trying to be a sports person. You teach the sports person certain abilities such as running, throwing a ball, or catching a ball, which is very generic, and then you can fine-tune their abilities towards a specific sport such as baseball or basketball by teaching them things which are similar but specific to particular sport. So in fine-tuning, that is what you will do with the model as well. As part of pre-training, you have sort of created a very generic model that has understood the general abstractions and semantics of the language. Now you want to fine-tune it towards a particular task. That could be creating a chatbot which is specific to medical use case. So you fine-tune the model on that particular data set and optimize towards the goal of the task that you want to train the model for. For example, we'll take the case of Lambda, where the model was pre-trained on a public dialog dataset and public web documents, and the task for which it was trained on was to predict every next token in the sentence given the previous tokens. Now, as part of fine-tuning, the model basically was fine-tuned towards generating the response in a conversational setting. For example, if you say hi, the model would respond with different responses. And then it was also fine-tuned towards identifying whether the likelihood of the safety, sensibility, and specificity and interestingness of the response that was generated by the model. So we basically fine-tuned it for 2 different tasks. Now here is a very high-level overview of the improvements that have been done. So if you look at the pre-trained model, the performance in terms of quality was improved when we fine-tuned the model by more than 10%. Similarly, in the case of safety and groundedness, the performance improved. We'll quickly move on to the challenges and the limitations. So LLMs are not perfect, and they come with there are some challenges in terms of training the large language models and deploying them in production for a particular use case. So they require a huge amount of computational resources. And so in most cases, what people do is they pick a generic pre-trained model that has been trained on similar data that they are planning to apply the language model for, and then you can fine tune it. So you don't have to pre-train the model yourself. You can just fine tune it on a smaller set of data, which is specific to your domain or task, and then start using the language model. And then there are costs in terms of deploying LLMs in production. One way to overcome that could be you can develop common APIs or interfaces that could be shared across organizations. So that way, not every feature, not every product is using a different LLM. Instead, everybody is sharing the same LLM, but could be different fine-tuned versions of the LLM. And LLMs also come with bias. They can inherit the bias which is present in the training dataset. As in, if your training dataset lacks certain content, then LLMs may not do well on those particular categories. And so one way to overcome that would be you can fine-tune on a diversified training dataset, and you can also conduct bias audits to mitigate the bias. Yeah, thanks. Just one quick, we are also hiring, so we are hiring for a variety of roles, so please feel free to reach out after the talk. Thanks.